Good morning, students. In this video, I'm going to explain the topic sharpening spatial filtering operation in image enhancement. So here, up to now, I have completed smoothing spatial filtering techniques. So okay, here in this video, we will cover the next topic, sharpening spatial filters. So this is nothing but here the main objective of sharpening is to highlight the transitions in intensity. So here what is the smoothing and what is sharpening we have covered in the last video. So smoothing spatial filters nothing but low pass filtering action, and sharpening spatial filtering is nothing but high pass filtering action. And that we know that what is the here low frequency component and high frequency component related to the images, right? So and then here low frequency component is nothing but small variations in the intensity, and which resembles the smooth area, right? So okay, smooth surface. Okay, now coming to the high frequency components. High frequency components means here sudden variations in the intensity, large variations in the intensity that resembles here edges. Okay, so that's why here in the smoothing spatial filters, so to smooth the particular surfaces here, that means here we just use the low pass filtering action, that is nothing but which removes the high frequency components, that means which reduces the effect of the large variations or sudden variations in the intensity levels, that is the edges. Okay, so that's why here the advantage is here which reduces the noise, but here due to the reduction of the sudden variations, that means the edges, it looks like a blurred image. Okay, so here is the next one. What is that? Sharpening spatial filter, that is nothing but the high pass filtering action, that means which removes the low frequency components, and that means which allows the high frequency components. That means here this is nothing but to highlight the what is that sudden transitions in the image, right? To highlight the sudden transitions in the image means to highlight the edges here. Okay, and also to reduces the small variation, small intensity variations. Okay, so that's why here what is the objective of sharpening, that is to highlight the transitions in intensity. So this is widely used in printing and medical imaging to the industrial inspection and autonomous guidance in military systems. So here in printing, that means to get the what is that clarity between the successive what is that symbols or letters like that, and also to highlight the letters. Okay, so that's why that means if you observe a particular thing, if you observe this one same sheet here as a newspaper like that, the printing purpose, that means here see this so many letters are there, those are isolated to the each one. Okay, successive one, and then this looks like here it is simply one example for the what is that one image which is having the high frequency components and low frequency components, right? See this, it is one image, right? So here this background is here whiteness, right? So here this whiteness is nothing but here which represents a low frequency component, small variations in the intensity. Am I correct? And then if you observe this one here, here is a white background, and here is a right one letter with the black color. Okay, right? That means here is a sudden variation in the intensity, right? So okay, here observe, it is nothing but a which looks like a edge. Am I correct? Right. So here to highlight this edge, right? So you should sharpen, we should highlight the what is that sudden transitions in the intensity. That is nothing but here sharpening the edges, right? So and then here this is nothing, that's why here this technique is widely used in printing and also medical imaging also, right? So in the medical images and medical image processing also, here we may use this particular sharpening spatial filters, right? And then industrial inspection. Suppose if you may take many examples here. Then you suppose if you take pipes manufacturing or cloth manufacturing or any particular ICs fabrication. If you take anything, right? So anything here to inspect the certain material for the checking purpose. Suppose if you consider as a pipe, right? So if in that pipe, if there is any small tiny hole is there, so how can you check here? So here that is not visible to our human eye also actually. Okay, so in such a case, that small tiny hole gives the here very black mark to the particular industry. So am I correct? If it is a gas pipe, maybe that tiny hole leaks certain gas also, right? So that's why here to observe that much, to observe, to inspect those materials, here we may use this type of image processing techniques. So in that, we may use this sharpening spatial filtering techniques. Okay, and then here in military systems for autonomous guidance also we may use this type of sharpening spatial filters. So many applications are there, very few added here. Okay, averaging is analogous to integration, so sharpening is analogous to spatial differentiation. Yes, am I correct? So listen here, averaging means low pass filtering action means is nothing but here we have used the average operation in the smoothing spatial filters. Okay, right? So you know that integration is analogous to this averaging action. So low pass filtering is nothing but integration, of course, and then which is applied on the smoothing spatial filtering techniques, right? So now coming to this one, right? What is that differentiation, right? So here differentiation here is nothing but high pass filtering action, you know that. So that's why here differentiation is applied on the images to sharpen the images. Okay, so here integration is used for the smoothing. So that means here integration means for continuous time, for the discrete you may consider averaging. That's why here averaging is for smoothing, differentiation is for sharpening. Remember this point. And then thus image differentiation enhances edges and other discontinuities and de-emphasizes areas with slowly varying intensities. It's a very important point. Image differentiation enhances the edges, right? So that means here we are using the high pass filtering action, that's why, which highlights the edges or which enhances the edges, right? So that means we can clearly observe the edges here. Okay, right? And then and other discontinuities also. Okay, so other discontinuities also means here maybe noise. That means in addition that means we desired edges. In addition to enhance the desired edges, it also enhances some undesired edges also. Those are said to be here noise. That means if we use a differentiation which enhances the noise, right? So and de-emphasize areas with slowly varying intensities. Okay, that means here which reduces the effect for what is that? Slowly varying intensities. What is the conclusion here? In smoothing spatial filtering operations. So here that one reduces the noise but increases the blurriness. But here in the sharpening spatial filter, that reduces the blurriness. Of course, reduces the blurriness or enhances the edges but increases the noise. Okay, increases the noise. Okay, this is the thing here. Here is one. So here observe this point. Okay, now here here the what is that here? Differentiation is used for the sharpening the one image. Okay, that's why here you should concentrate on differentiation. So here is a first order derivative and then second order derivative. Okay, very important one. So here is a very important basic thing here. You should know this. We just apply this on the image, or first order derivative technique or second order derivative technique. One is said to be here Laplacian operator, another one is said to be gradient operator. Okay, it's okay. Now coming to the first order derivative. What is the definition for the first order derivative for particular any image here? So here observe, it must be 0 in areas of constant intensity. What is that here? In the image, if there are any particular, if there is any area which relates to the constant intensity, right? Constant intensity means if the intensity value is 5, throughout here certain area is having the value, what is that? 5 only, 5, 5, 5, 5 like that. Okay. So here if you apply the first order derivative to that particular region, a particular area, then you can get the 0 value. Obviously you know that what is the here the first derivative of the constant here, d by dx of x, what is that, some constant c, d by dt of c, like that, what we can get 0. Obviously that's why here in the image, right, if there is an area consisting of what is that constant intensity, then you can get the 0 value in that particular corresponding location, okay, or area. Okay, that is the first point. Okay, then next one is must be non-zero at the onset of an intensity step or ramp. Okay, that means here at the onset of an intensity step or ramp means a sudden you know the step signal and ramp signal, what is the nature of the particular step and ramp, of course. So onset of an intensity means here, so variation, right? So to go to the step here, so here is a change from low to high or high to low, so that is the onset value. And also ramp also, that means here growing ramp or decaying ramp, that means here the value is changed from one value, right? That is said to be discontinuity maybe, right? So that position is called as onset here. That means if you apply the first order derivative on particular position, then you can get the non-zero value. And also next coming to the another nature, what is that? Ramp, right? So ramp means here is continuous thing, right? 1, 2, 3, 4, 5 like that, or 1, 4, 8 like that. That means some values are what is that? Slowly increasing or slowly decreasing. So here if you apply the particular first order derivative to that particular ramp, what we can get ramp nature means like x, right? So that means d by dx of x means, so here you can get the value like that. So that is the not a 0, that is the non-zero value. Okay, right? For the step also, that means here the some value is you know that the d by dt of u of t is nothing but del of t, right? So that's why here at the discontinuities also you can get the non-zero value, not the 0 value. That means if you apply the first order derivative operation to the particular image, so here you may segregate the image like this, right? Some area is like a, it is having some constant intensity, or it is having some what is that ramp nature intensities, and also it is having some sudden changes like onset of an intensity step or onset of intensity ramp like that. So here if you segregate the image like this, if you apply this first order derivative operation, then you can get the resultant values, resultant intensity values like this. Okay, right? Now coming to the second order derivative. So here for a second order derivative, the definition is it must be 0 in constant areas, right? So same thing like in the previous first order derivative. Next one is it must be non-zero at the onset. The same thing, it must be non-zero at the onset, right? So that means onset of an intensity step or ramp. And now coming to the next one, it must be 0 along ramps of constant slope. That means for first order derivative to the ramp, you can get the non-zero. That means d by dx of x is the constant. But again, if you if you do the differentiation to that particular constant, you can get the 0. That's why here double derivative of the or second order derivative of the ramp gives the 0. That's why it must be 0 along ramps of constant slope. So this is the difference between the what is that? First order derivative and the second order derivative. And of course here first order derivative means here d by d x or d by dt like that. Here variables are x and y. That means here you have the two derivatives. One is along the x direction and along the y direction, d by dx and d by dy, right? So horizontal way and what is that, vertical way, otherwise row wise, column wise, right? So d by dx, d by dy, right? Here for one dimensional function, if I take f of x like that, not the two dimensional, so consider like this, one dimensional signal is the f of x. What is the d by dx of f of x here? Here first that means for the discrete function, so d by dx of f of x is nothing but f of x plus 1 minus f of x for the discrete signal. Okay, right? So that's why here use the formula. What is that? Differentiation, first order derivative of the particular f of x is nothing but f of x plus 1 minus f of x. Remember this formula, this is very important. For the second order derivative, d by dx of what is that? D by dx of f of x. That means d square f of x by dx square is nothing but f of x plus 1 plus f of x minus 1 minus 2 f of x, right? Right? So this is for one dimensional. So okay, you can easily assign to this one to the two dimensional function also, right? F of x comma y means here d by dou x, or we may take dou y, right? So if it is f of x comma y, so here you should complete the derivation, what is that, differentiation in both axes. One is the x axis, another one is the y axis, or one for x variable or y variable. That means d by dx of f of x comma y is nothing but, what is that? Here y is the constant one. That's why f of x plus 1 comma y minus f of x comma y. D by dx, d by dy of f of x comma y is nothing but f of x comma y plus 1 minus f of x comma y. Like that, you may here put some constant variable here. Okay, so that's why that's only difference. So okay, here the next one is nothing but illustration of the first and second order derivatives. Okay, right? So that means here observe this one. This is the one scan line, right, for one image. So here consider one image. So in the take one scan line, any line along the x direction. Okay, so one row. Okay, so that means here observe the take the intensities. Okay, that means here the intensities are like that. So along the x direction, 6 6 6 6 5 4 3 2 1 1 1 1 1 6 6 6 6, like that. So this is just an example. Consider this is the one scan line taken from the 2D image. Okay, this is the 1D line now. Okay, now here draw the graph, right, for this what is that, intensity values along with the x. Okay, right? So here intensity values take on a y-axis and here is the on x-axis here. So consider this one. Okay, 1 unit distance. So that means here here in this position, what is the intensity? 0. After 1 unit distance, that means if it is a x, next one is x plus 1, next one is x plus 2, next one x plus 3, like that. If it is 0, 1, 2, 3, 4, 5, 6, 7 and so on, like that. Okay, now here at this position 6 and then see these intensities and then mark the points here. Okay, establish one graph. Okay, now observe. So here see this 5, 4, 3, 2, 1, next again 1, 1, 1, next one is 6, 6, 6, 6, like that. So observe here, right? So here this is nothing but constant intensity, like this one, either this one or this one or this one. Okay, now what is the ramp position? This one, slowly varying the values like this. Okay, this is nothing but ramp. Now where is the on-step, what is that onset values here? This one, this is the onset intensity transition and this is the onset. This is the onset. So changing the value, right, from one value to the higher value with the sudden change. Okay, this one. These are the onset step. This one is onset ramp, like that. Okay, so here in this way just draw the graph, right, and then here apply the first order derivative and the second order derivative, right. First order derivative means, so here take the formula f of x plus 1 minus f of x. Second order derivative means f of x plus 1 plus f of x minus 1 minus 2 f of x. Okay, so take these two formulas here. So here for first order derivative, what is that? F of x plus 1 minus f of x. Here, that means here, that's why I just start from this position. Okay, here, what is the derivative? Now, f of x plus 1 minus f of x. That means 6 minus 6 is nothing but 0 here. Okay, next one is, right? So, for this, at this position, f of x plus 1, what is that? Minus f of x. That means 6 minus 6 is 0. Next, here, for this, f of x plus 1 minus f of x. What is that? 5 minus 6 minus 1. So, that just to do the difference, subtraction between the successive values. Okay, 5 minus 6 minus 1, 4 minus 5 minus 1, 3 minus 4 minus 1, like that, 1 minus 2 minus 1, 1 minus 1, 0, like that. Similarly, 6 minus 1, 5, like that, 6 minus 6, 0, like this. Okay, observe these values and then mark these values in the resultant one. So, what is the first derivative of the 1D scan line? Or scan line for the image? Here, see this, like this. Okay, so here 0, 0, next one minus 1, next one is minus 1, minus 1. Black dots indicates the first order derivative. Okay, here see this, black dot indicates the first derivative, square box denotes the second order derivative. That's why here, so see this. Okay, now 1, next, like this. Okay, like this you can get the values. Okay, so that means here, observe here the nature, observe here. So here the intensity variations are like this in the image. After applying the first order derivative, so how it will be? My image, see this, like this. Okay, so for one scan line, observe, and then imagine this one for the all scan lines, for all rows, either rows or columns. Okay, so see here. Okay, for constant intensity, so the value is 0. So here onset values are slowly change in intensity is like ramp. So here you can get certain value, small intensity value, and after that here for constant intensity again 0, and then here is a change, right? So it is here actually edge here. The value is changed here from low value to the high value. So here this one is said to be edge. Am I correct? This is a smooth surface, right? Smooth surface. Am I correct? So here is a small intensity variations. But here edge means here, so this position. Am I correct? So that means here, so at this mode here, what is that resultant one here? See this? The value is increased like this. Okay? So then again, the value is here. Now again, it's a constant. For constant, 0. That means by observing these intensity values, right? So what is the conclusion here? Edge value is highlighted. Okay, edge value is highlighted. So remaining values are suppressed. Okay, so here also you have the 666 intensity, right? So here also you have the 6 intensity. For both cases, what is the change here? This is a smooth surface. That means the low frequency component, right? Low frequency area. This is nothing but high frequency area. By using this, what is that operation? You should enhance the edge area and you should suppress, you should de-emphasize the constant area. Am I correct? That's why here see this. So here is a values are so suppressed, right? Am I correct? But now here value is highlighted like this. Okay, right? So in such a way you can highlight the edges. Okay, right? And then coming to the second derivative. Second derivative means here, see that what is the formula here? So use the formula like f of x plus 1 plus f of x minus 1 minus 2 f of x. Okay, use this formula. Okay, so that means one is the previous pixel and then one next pixel, and then add those two and then subtract 2 into present intensity value. Okay, right. So add these two intensities, minus 2 into present pixel. Remember that formula and then apply here. Okay, see here. What is that? 6, then 6, 12 minus 12. Am I correct? 6, add these two values, 12. Then multiply this value with the 2. What is that? 2, 6 are 12. So 12 minus 12, 0. Now coming to this one. Now same thing. Okay. Now if you observe here, What is that? 4 plus 2, 6 minus 3 2s are 6, 0. Here observe 6 plus 5, 11 minus 12 gives the minus 1. Like that, just do the calculation and then you can get the values like this and then draw the graph here. Okay, see this square boxes, right? So here the square boxes are appeared like this. See this. Okay, right? So what is this here? At edge, if you observe at edge, so here the point is located at the same value. What is the previous first order derivative value? And of course here this one, so immediately, so suddenly dropped to this value 0, right, in the first order. But in the second order, it goes to the again another peak. What is that? That means a double edge like that. Double value. Am I correct? Right? So here is a one peak and here is another peak. Right? So instead of sudden suppressing from higher value to this one, here at the edge, it gives the double values, double high transition values. Am I correct? And then goes to the 0. So okay, observe here this difference. This is nothing but 0 crossing. Right? 0 crossing is there in the second order derivative. Okay? Right. So here, that means here you may apply first order derivative or second order derivative to the particular image. Then you can get the resultant image, right? So with the high transition values at the edges. Okay, am I correct? If there is a constant intensities, so those values are here very, what is that? De-emphasized. Am I correct? So okay. That means here, see this. Right? So first order derivative or second order derivative. So here conclusion. So here which one is better actually? We will get the conclusion here. Right? So what is that? Edges in digital images are ramp-like transitions in intensity. Am I correct? In which case the first order derivative of the image would result in thick edges because the derivative is non-zero along a ramp. Okay. On the other hand, the second derivative would produce a double-edged 1 pixel thick separated by the zeros. Am I correct? So now what is the conclusion? The second derivative enhances fine detail much better than the first derivative. So that is a property that is ideally suited for the sharpening images. So that means here what is the conclusion here? So for providing this double-edged one, right? So this one for this facility, and then you can here is a what is that? Very large thickness, so when compared with the first order derivative. So that's why here the second derivative enhances a very fine details also. Fine details. Okay. So that's why it is if you want to enhance the very fine details, you may apply the second order derivative. So otherwise you may apply first order derivative. And also one more advantage is second order derivatives are very much easy to implement. Okay, so right, so implementation purpose also when compared with first order derivative, so second order derivatives are much easier. Okay, this is the conclusion. Okay, right now here that's why here we just start with the second order derivative. Later we will discuss the first order derivative. Okay, so now coming to the second order derivative, which is also called as Laplacian operator. So here under this what is that? So okay, coming to this second order derivatives, that is also called as Laplacian operator. Okay, so now here how can you get the second order derivative for the image? So here by using this Laplacian operator formula, right? So del square f is nothing but dou square f by dou x square plus dou square f by dou y square. This is the formula. Based on this, first you should complete the dou square f by dou x square and dou square f by dou y square. So here for a 2D function or 2D image, it is nothing but f of x plus 1 comma y plus f of x minus 1 comma y minus 2 f of x comma y. So here with respect to y means f of x comma y plus 1 plus f of x comma y minus 1 minus 2 f of x comma y. So add these two, then you can get the Laplacian operator del square f like this: f of x plus 1 comma y, f of x minus 1 comma y, f of x comma y plus 1 plus f of x comma y minus 1 minus 4 into f of x comma y. That means here del square of operator is nothing but here f of x comma y is multiplied by the minus 4, and then here f of x plus 1, this one, these 4 are 4 neighbors of this f of x comma y. Am I correct? 4 neighbors, right? So here 4 neighbors are multiplied with the 1 coefficient. Am I correct? That's why here based on this equation, so we should develop one mask. So that mask is nothing but, so which has some weighted coefficients based on this equation. So then you just apply this mask to the image. So then here that means do the neighborhood operation, and then you can get the second order derivative operation. Okay, right. So that means you can get the enhanced image. Okay, right. So then here that means, so that means here in this way you can develop the mask, okay, based on the del square f operator. So okay, here say this here, what is that? F of x comma y is multiplied by the -4. Am I correct? This one. So that's why here center pixel or center what is that, weighted coefficient at this center position is nothing but -4, and 4 neighbors are having the 1 intensity, and then here so diagonal neighbors are, there are no diagonal neighbors here. So for the f of x comma y, that's why here the weighted coefficients are here 0. So in this way you just develop the mask based on this equation. Then here do the neighborhood operation, and then you can get the, what is that, enhanced image with the second order derivative operation. Okay, so like that here you may use this one, either this one, or so a simple change here. You may use here positive weight here, and then here apply the negative sign. Okay, so just reverse of this one. So you can do this one also. Otherwise, and then you can take the another thing. What is that? So give the more weight to the actual pixel. What is that? So f of x comma y. So more weight to this, and then just give the here what is that, diagonal neighbors also, right? So you may use this one also, that is the enhancing of this one. What is that, next level of the mask here? Okay, right? So if you want more better when compared with this, then you can use this type of mask also, and then you can use this one also, just inverting the sign here. Okay, so this one also here. So I'm giving here 4 different masks here. I'm as an example here to do the second order derivative operation. Okay, or to develop the mask. Okay, filter mask. Okay, so these are the 4 different masks here to do the Laplacian operation. Okay, so now here what is that here, enhanced image? How can you get? So based on this mask, right? So you can get the, what is that, one second order derivative image. But to enhance the image here, you should apply this one. This is the enhanced image g of x comma y. So after getting the second order derivative image, right? So then here this is not the actual enhanced image. You just do this operation. What is that? Take the original image and then do the here what is that, addition, actually addition, right? So if you use this particular mask, right? So consider these two masks, or consider these two masks. So here observe the center pixel is here with the -4. Here is the center pixel is with the +4. That means one is the positive, another one is the negative. So see here, if the Laplacian mask is positive, that means add these two images. Okay, so after getting second order derivative, okay, then just add this one to the original image. If the what is that, center coefficient is having with them negative, then subtract these two. That means here subtract these two images, then you can get the g of x comma y. Okay, so that's why here you just use the original image and the second order derivative operation, what is that, resultant image. Then so do this like this, then you can get the, what is that, enhanced image. Okay, right? So in this way here consider this one as an example. So this is the blurred image. Okay, so this is the north pole of the moon, right? This is the blurred image. You if you want to enhance the what is that, highlight the, what is that, edges here. So here you should apply the Laplacian operator, that means second order derivative. So that means here without scaling, that means here what is that, based on the this one. Okay, this means without scaling, this means with the scaling. Okay, right? Now without scaling, if I use the without scaling, so you can get the second order derivative resultant image like this. Okay, with the scaling you can get the image like this. So observe the changes here. Okay, right? Now here by adding these two, you can get the image like like this. So observe here how the edges are here sharpened. Okay, so keenly observe here how the edges are sharpened. Okay, right? So and then here observe, if I use this particular mask, then if I add particular what is that scaling mask to this image, then I can get the second order derivative resultant image like this. Then if I add these two, I can get this one. So here also observe the variation between these two. So here say this how the edge is very much highlighted in this one when compared with this one. Okay, right? Am I correct? So that's why here if you want to highlight the, that means if you observe these two images, so here is a blurriness. Is there any blurriness here? Observe? No, right? To reduce the blurriness, you should use the sharpening. Okay, that is the thing. That means if you want to reduce the noise, use the, what is that? Smoothing. So, but smoothing gives the blurred image. After applying the sharpening, you can get the good enhanced image. Okay, am I correct? This is also one of the technique. Okay, it's okay, right? Now coming to the unsharp masking and high boost filtering. So it's a another technique here to sharpen the signal. So here remember these words, unsharp masking and high boost filtering. So this is nothing but here consider the original signal like this. Okay, first do the blurriness, right? First do the blurriness. Blurriness means what is that? Sudden transitions, right? Sudden transitions are there. Those values are here adjusted, okay, to the constant intensities or to the smooth small variations in the intensity. That's why here is a sudden transition. So that value is reduced like this. Observe this one. Here also this value is reduced like this. That's why here this is the blurred signal. Now use the unsharp mask like this. Unsharp mask. How can you get the unsharp mask here? Subtract this blurred signal with the original signal. Then you can get the unsharp mask like this. Okay, take this one minus this blurred signal. Then you can get the unsharp mask like this. So you just add this unsharp mask to the, what is that, original signal, right? Original signal. Then you can get the resultant signal like that. Am I correct? Then, so what we can do here, just highlight the, what is that, edges, right? Like this. Then you can get the, what is that, sharpening image. Okay, this is one of the technique here. So here, this is the same thing here. Here, if the scaling factor is 1, that is the unsharp masking. If the scaling factor is greater than 1, that is the high boost filtering. Okay, that's it only. So see this here, the method. First read the original image, then blur the image, that is f dash of x comma y. Then develop the mask like f of x comma y minus f dash of x comma y. Then add this mask to the f of x comma y. Then you can get the g of x comma y. Okay, right. So this is nothing but unsharp mask. Very simple one. Now coming to the high boost filtering means the same thing here. Here follow the 1, 2, 3 steps. Develop the mask, and after getting the mask, use the some coefficient here. That means k greater than 1. Here k is 1. If k is greater than 1, then it is said to be high boost filtering. If the k is greater than 1, that means you can get the, what is that, high sharpening, okay, at the edges. That's why here there is high boost filtering. Okay, so this is the one here, one of the procedure to do the sharpening. Okay, right. So now coming to the first derivative, that is said to be here gradient operator. Second order derivative is said to be Laplacian operator. First order derivative is said to be gradient operator. What is that here, gradient operator? Del f. Del f means gx, gy. So here this is dou f by dou x, dou f by dou y. Gx is the dou f by dou x, gy is the dou f by dou y. Del f is nothing but magnitude of this del f. Okay, what is that? So we need the first order derivative or gradient operator. This is nothing but this gives the what is that, vector one, but you need the only scalar value. So that's why here after getting this one, so just to take the magnitude value of this one. So what is the magnitude value of this one? So after doing dou f by dou x and dou f by dou y, those are nothing but gx, gy. Just take the square root of gx square plus gy square. So now this is nothing but this one. Okay, so actual formula. Okay, that means after doing dou f by dou x, dou f by dou y, use this formula. What is the square root of dou f by dou x whole square plus dou f by dou y whole square. Oh, here this is the problem here for implementation. What is this here? Here so many operations are there. So you should first do the differentiation, and then squaring of the particular thing, and then addition, and then square root. Square rooting is very difficult here. So here it gives more steps also. Okay, that's why here for simplicity, this one is almost equal to, approximately equal to mod of gx plus mod of gy. So right, mod of gx plus mod of gy, it is very simple when compared to these operations. That's why here you just consider the formula for the first order derivative or gradient operator like this. Okay, this is the actual one, accurate one, but this is the approximate one. Del f is nothing but mod of gx plus mod of gy. That is said to be here m of x comma y. Okay, so do this one. So now that means that is nothing but dou x by dou y, take the mod value, then dou x by dou y, take the mod value, and then add these two. Then that is nothing but gradient operator or first order derivative operator. That means here consider one image here, that is the 3 by 3 image. Consider like this. So now here these are nothing but masks. Okay, right? The first one is developed by robot. Here robot, the next one is developed by Sobel, right? So we have different operators here, robot operator, Sobel operator, private operator, right? So those are developed by the different authors or different researchers, different scientists. Okay, that's why here the first one is here initial one is the robot cross gradient operator. Based on this particular here, so what is the dou f by dou x? We already noted that one. What is that? Dou f by dou x is nothing but f of x plus 1 comma y minus f of x comma y. Am I correct? What is the dou f by dou y? F of x comma y plus 1 minus f of x comma y. So that's why here if you add these two here, so here, so then what is that here? So that means here is a two different what is that differentiations, right? One for x, another one is for y. Okay, this one is for x and this one is for y. So we should develop the two marks here, one for along x direction, one for along y direction. Okay, so that's why here see this, these are said to be cross gradient operators. Okay, so cross gradient operators means here based on the f of x, what is that? F of x plus 1 comma y minus f of x comma y. If it is f of x comma y, then so here the next one is said to be, what is that? F of x plus 1 comma y. So that is the minus of f of x comma y. So this one, right? That's why here, for here minus 1 1, here 1 minus 1. So see this one in the example, you can understand that one clearly. See this here. Okay, now see this. Right? So what is the del f here? Here based on the gx and gy, you should find out that one. Okay, this is the particular image. Okay, right? So here gx is nothing but z9 minus z5. Okay, gy is nothing but z8 minus z6. Cross gradient operation. Okay, see this. Okay, so here one is the gx, that is z9 minus z5 according to the robots. Another one is z8 minus z6. That means dou f by dou x is according to him z9 minus z5. F of x plus 1 comma y, what is that? Minus f of x comma y. You may use that one or you may use another thing also, right? So here they developed their own what is that differentiation. So that's why here this is the one. Okay, gy is z8 minus z6. That's why that is said to be robot cross gradient operations. Okay, now here based on the exact equation you should develop this one to get the del f. But for the approximation, for easy to implementation, so here use this one. Okay, so this one. So that's why here the masks are, okay, right? Mask, right? Like this. Okay, this one. Based on that formula. Okay, and then now the next one is the Sobel operator. Okay, what is that? Sobel operator. So this is nothing but Sobel operator. So that is here added. So see this. So using the equation, he developed his own equation. What is that? Del f is equal to like this. Okay, then from this you can easily develop the mask like that. What is that? One is along the x direction, another one is along the y direction. This one is for the x. So that means here according to this here z1, z2, z3, z4, z5, z6, z7, z8, z9 are there, and then use the coefficients like that. Okay, so here z8 coefficient is 2, z7 coefficient is 1, z9 coefficient is 1, and then z1 coefficient is minus 1, z2 coefficient is minus 2, z3 coefficient is minus 1, and remaining coefficients are here 0. Like that here. So just develop the particular mask for one x direction and the one for y direction. So observe here also. According to him, he developed his own equation and then he developed the masks and then he just use the particular what is that these masks, that means neighborhood operation by using this mask. Then so you can get the first order gradient resultant image. Okay, so then you can get the enhanced image by using the first order operator. Okay, this is the another technique. So here remember the first one is the what is that, Robert, and second one is the Sobel. Why here Sobel? Here Robert, in Robert, so here you can get the one confusion. So where is the center position, right? So 2 by 2 matrix gives certain what is that ambiguity to you. Okay, so right where we can place this one to on the original page, right? Original what is that image, right? So where to understand the what is that exact position f of x comma y is very difficulty, right? That's why here, so to what is that, to avoid that ambiguity, so from the 2 by 2 size of image, so we just go to the 3 by 3, right? Now this is the center position, right? Okay, right? So that's why here to avoid this ambiguity, so yeah, we have to what is that take the Sobel's method and also Privet method also, right? We will discuss this one again in the image segmentation. Okay, right? Now here this is the example. So here take the contact lens original one. So if you see this one, you cannot identify the what is that defect here. Okay, right? So but if I get the what is that sharpening of this particular image by using the Sobel, so that see this, I can easily highlight the what is that edge, then I can easily identify the defect. Okay, right? So this is the one of the example for the gradient operator. Okay, right? So this is about what is that sharpening spatial filter. Okay, thank you.